So I'm Steve Scargall. I'm the Senior Software Architect and Product Manager at MemVerge, working on a lot of the solutions that you guys are just asking questions about. So we'll cover some of the questions that were asked earlier about how do we provision CXL and what it look like to an operating system. How does an application consume that? And then we'll tuck into some of our solutions, Memory Viewer, Memory Machine. So we'll start with provisioning CXL. So there are currently a couple of ways of doing it. If you're familiar with how we did things with, say, the Intel Optane product, a lot of the commands solutions are very similar. So I'm showing one option here, and this is the BIOS mode. So this is an AMD platform, for example. It could be an Intel platform. It doesn't really matter. But there'll be some BIOS options in there that you can change the behavior of how CXL is mapped up to the operating system. So the one on the left-hand side, the user managed, the intent here is that we, as a user, or potentially as the MemVerge solution, want to manage the CXL memory independently of the DRAM that's already available to you. So we don't want the kernel to touch it. We want to manage the memory allocations for you. The kernel managed is, okay, we'll just treat CXL like we do with DRAM. We'll put everything into the basic bucket, the zone normal. The kernel can manage it. The applications don't really care too much. The difference on the user managed is that we want to try and manage the devices using device stacks. So again, with the Optane, device stacks is just a memory mappable system call into the device stacks. The application can then access that memory directly, do its load store operations exactly the same as it does with DRAM. The intent is that we get these memory-only or CPU-less NUMA nodes that you can see bottom right. So that's just a one-socket system with some CPUs, some DRAM on node 1, and on node 0, and then node 1 is the CXL memory. Now, we can also emulate this. So if you're not as lucky as us to work with the partners and you don't have access to hardware right now, you can emulate CXL using the rule of thumb that CXL is approximately 1 NUMA hop away. And on a 2-socket system, that's pretty trivial. You can just turn off the CPU cores, play with the on-call frequency, and that remote DRAM is effectively a CXL module, right? Now, we can also do very similar things with QEMU, the emulation software, and KVM. I will say that the work that we're doing with the community and the community at large is ongoing. So if you want to get all the bleeding edge features, you have to get bleeding edge code, which means you either have to compile it or grab patches from the kernel and QEMU. But fundamentally, it is fairly trivial at the moment to emulate QEMU as a pass-through into a hypervisor environment. I will say it's not very performant. It's not the intent right now. It's just functional. But if people want to get involved in this and accelerate this area, we would love some help, even if it's just kind of looking at some patches and commenting on that, right? So let's talk about the application side now. So how will applications consume CXL memory? And I'm specifically talking about the type 3 memory, the memory expansion, the memory pooling here. We're not talking type 1 or type 2. So like we said before, right, it's just memory. Appears as memory, you can use it as memory, you can do whatever it is as you do with memory. So you can use a NUMA control Linux utility to say to your application, use NUMA nodes X and Y, or use CPUs from whichever NUMA node. Or if your application is already a NUMA aware, you can use the libNUMA interfaces as well. But there's a but. There's always a but. And we've kind of described some of the challenges already with the previous speakers, but the NUMA nodes could be completely different characteristics, right? I'll show you a diagram in the next slide. But they might have different latency characteristics, different bandwidth characteristics. They might be different media types. And the application doesn't really know. All it knows is, here's some NUMA, I can use it, yes or no. So the question comes back to, can a non-modified application, or should a non-modified application use CXL in these areas? So this is the diagram that kind of illustrates this. So we'll start at the lowest level first, the hardware. The DDR, the CXL backed by DDR5 and CXL backed by DDR4, those are intended to be kind of like Ahmad showed, right, installed locally in the host. They're 1 NUMA hop away. The latency is pretty close to DRAM. Applications probably use them without any modification. Now, what if we take that same media and we put it in the JBOM? Well, we've now extended the distance between CPU and memory, so the latency has gone up. The bandwidth might stay the same, assuming you're using by 4, by 8, by 16. So that gives you a different characteristics of that particular NUMA node or NUMA nodes. And then we move into CXL 2.0 that we just heard about. Right now we're getting into single level switches. Now that's going to add distance, latency. The bandwidth's going to stay the same with using by 8, for example. And as we get into 3.0 specification devices in the future, now we've got multiple levels of switches. So we don't know then if that memory is in a JBOM or an appliance that's in the same rack as us, or in the rack next door, or in a pod down the row. All of these things are going to be coming down, and that's going to change the characteristics of the memory that is mapped to the application. So thankfully, we have a solution. So this is a bit of a teaser into what I'll be talking about later, right? But the MemVerge memory machine, as we call it, has different features, functionalities, data services. So with our elastic memory data service and our tiering data service, we can abstract all of this hardware intricacies away from the application and effectively just give the application what it thinks is memory. Virtually the same. It's a consistent virtual address space that may or may not be mapped to one or more different types of memory with different characteristics under the hood. But the key here is that we're making this transparent or opaque to the application layer. So now unmodified applications can absolutely take full advantage of high memory, high bandwidth, low latency devices that are available. So with that, I'll talk briefly about our 3 core products: the memory viewer, the memory machine, and the composer. So Craig, you asked the question about how does all this stuff get composed. We call it a composer. You can call it orchestration. You can call it a global fabric manager. All those terms are synonymous effectively, but we're aiming to be able to control this mass of devices that is at rack scale. So the memory viewer has been available for a while. The intent of memory viewer is to show you as a user what your applications are doing. So today you can go in, you can look at a process address space and see how much resident set size it has and how much memory it's using, etc. But the key question for heterogeneous environments is how much of that memory is actually hot and how much of that is cold, i.e. could we, under memory pressure situations, move that to a lower tier without the application having to do that for you. So that's the intent of this of memory viewer, is that we will work in a DRAM environment. So we'll show you what your application is doing today, how much memory of that is hot, and we can take that information and then start to architect a CXL environment saying, I could use a 2-to-1 or a 10-to-1 ratio of DRAM to CXL because I know my application's only using a certain amount of memory that's frequently accessed. So here's some screenshots. This is of the old interface. I don't have anything of the new one yet, but on the left-hand side is the topology. So we're showing a 2-socket system with 2 DDRs involved. And underneath, we're just showing a CXL bus with 4 CXL devices attached. On the right-hand side, you'll see the bandwidth, reads and writes for DDR versus CXL. And then here, we're showing that we can drill down and go, well, for each process, we can show you exactly how much of the memory you're using, how much of that is hot, and we'll run this for a while, and then again architect the solution that's best deemed for your environment. So choose your device vendor, choose your switch vendor, choose your characteristics of the device. You want by 8, by 4, by 16, right? So this is kind of what we're using to get you into a CXL world, and then when you're in the CXL world, well, we just continue to use memory viewer and continue to show that you're doing the right thing. And in fact, some of the things that we're doing in our memory machine utilize some of these metrics to make sure that if we're moving memory around, that we're doing the right thing. We're not making things worse. We're always trying to make things better or keeping the performance consistent.
I have a quick question there.
Sure, go ahead.
Just in terms of visibility there, it's good that we can see usage and bandwidth.
Mm-hmm.
Are there any plans to incorporate latency? As we start adding more tiers of memory here, high bandwidth memory, DIMMs, CXL attached, 1 hop, 2 hops, etc. That will become a meaningful statistic.
It absolutely will be, yes. But of course, we're reliant on the CPU to tell us that. And at the moment, the current generation of CPUs don't have those hardware counters integrated to extract the latency. We can measure it from an application layer from user space and get that information. But ideally, we would like that to be part and parcel of the hardware abstraction layer. So yes, we can just go from a software perspective, go write a CXL stat tool, for example, that's very similar to IOstat and VMstat and everything else. It'll give you those sorts of metrics. Otherwise, it becomes a bit of a software overhead to try and manage all of that right now.
So, MemVerge, if I'm correct, so you can install that pre-CXL to see what's happening, and then afterwards, you can actually see the results. So in a sense, it says like create a baseline kind of comparison.
Precisely, pre and post CXL. Yep, exactly. And we're offering this, the version that's on our website is free. It's not CXL compatible yet. It was really intended for DRAM and Optane. The CXL version is coming pretty soon. So exactly that.
So if you were to challenge the developers, perhaps you could ask the software developers, firmware developers to provide accurate SLIT tables as part of ACPI to reflect at least the unloaded latency more accurately in the form of different NUMA domains.
Yep.
And then, of course, the loaded latency might be different, and that's the one that you could measure during runtime.
Yeah, precisely.
Yeah, just one step at a time. We need to get to the hello world and then enhance the capability.
Yep. Yeah. But
I'll help you get back. I'll help you get back to your. You don't call it orchestration. You call it. Was composer.
Composer.
Are you doing any work here around optimizing those memory tiers within the composer here? Because again, we have different levels of memory, different latencies. You know, if we look back at storage, again, you know, prefetch was the thing. We're fetching memory from slower storage, or fetching data from slower storage and caching it. Was an overall benefit to system performance? Are we taking a similar approach here with RAM?
Yes, but it's not caching, it's data movement. Because technically, you could access the data in place, it's still memory, it might have some higher latency for that first hit. But as we identify that that access is becoming warm, yeah, we can move it up the stack here. And in fact, if we go back, I didn't necessarily call it out, but over on the far right-hand side here, we have this intelligent data tiering that keeps data, hot data, in the best tier. Now, having said that, of course, this opens up new opportunities. So the goal isn't always to move hot data up to the fastest tier. It might be that cloud service providers offer different types and classes, characteristics of memory, right? So you can think of a cloud service provider offering maybe a platinum, gold, silver, bronze type of memory, meaning the data tiering stops when you hit the type of memory that you're allowed to access. So your platinum customers, sure, access DRAM, no problem. Your bronze, your silver, your gold might stop at local CXL, right? Because it has different cost characteristics, different bandwidths, etc. And the application might just run fine without any problems, right? But now, like Charles said, right, you've got these two knobs to play with. You can access the number of cores that you want and the type of cores, but also the memory and the memory types and the characteristics that it has. So cloud offerings are no longer restricted by, well, you want to go up in the memory count, now you've got to buy more cores to go up that because the shapes and the instance types are fixed. Here we can say, well, stick with the number of cores or downgrade the number of cores, but bump up the memory, or vice versa, right? You can play with each one as you see fit.
So another challenge for the developers, not only latency but bandwidth might be different. So in the tables that people create, bandwidth could also be sold in a different way. Latency can also be sold. Persistence versus not, robustness of memory, if something's local versus remote, how robust they are, memory repair characteristics, all of those attributes could be described so that it could be used and then later sold to different customers.
Exactly.
So we're back round to you have to understand your applications.
To some degree, yes. Yeah. I mean, as an interim layer, right? I can't disclose too much under NDA, but yes. So we'll have policies and recipes and things like that that say guide us, right? Give us some hints, give us some guardrails around what we should and shouldn't be doing.
Well, there's I just brings up two comments that I can think of. The first is that whatever your load balancer is going to be using memory bandwidth as well. So you've thrown something into the mix that is potentially competing for resources with your applications. And you need to come up with some pretty elaborate eviction algorithms when you actually move things into higher tiers. I mean, figuring out where to evict stuff that wasn't at higher tier 2 is going to be more than just a, we don't need it in cache anymore type algorithm.
Yes. Well, and you mentioned plural, right? Algorithms. There isn't just one solution here, right? There are many ways of moving data around, many ways of identifying hot and cold data. One algorithm might work great for databases. It might work rubbish for web servers or whatever else, right? So we're developing lots of different algorithms, I should say, and you'll get to pick and choose which one you would start with. Now, it might be that we can change algorithm partway through because your workload during the day is different than the workload at night. Might be that you just need to switch algorithms at that juncture, do your batch processing, and then switch back for the daytime, right? So it's not static. So with that, we've already mentioned some of this anyway, right? But the N-level, N-way tiering, right? The kernel can do tiering today. It's just two-way. So you either pick two different types of media and it'll handle that. The previous diagram showed we can do N types of media, so we need to do N-way tiering here. The elastic memory is kind of what we were talking about with the composer, right? How do we map memory up to a host, and what happens during runtime if that host needs more memory or less memory to deal with stranded or frigid memory, right? So that's thin provisioning effectively of memory, like we have with storage. You can overcommit, and once you hit a threshold, we'll just give you the memory that you really need. And again, that's a cost efficiency saving for the infrastructure guys or potentially for the cloud guys as well if they want to offer that. And there's also different types of memory, different types of devices, right? Single logical devices, multi-logical devices, dynamic devices. So the ability to right size the CPU and the memory for the workload at hand is pretty critical, and that's what we're doing. Snapshots, we've been doing that for quite some time. That's a very popular feature that we have. So the ability to not only take a snapshot of what's on disk, but also the running state of your application, right? So everything including memory, the CPU registers, the whole kit and caboodle. And then when if your application crashes or you want to move it to a different instance, again, move up or down on the instance scale, we can do that. Sharing, Charles mentioned this earlier. This is a super exciting area, actually. This opens up a ton of research areas and exciting projects because you're deduplicating data. You don't have to have hundreds of nodes all with the same copy of the data, right? Now they all just go to a shared pool and that's your data set. So that saves on DRAM in the host. That's a TCO cost saving. You might be able to do a host consolidation exercise. So that's a sustainability angle, a cost angle as well.
At the same time, you run into overhead because you actually need the free space to be able to do those zero copy buffer or zero copy.
Well, what I mean is zero copy, so you don't have to do data shuffling or across the network because host A wants some data and host B has it and everything else. It's zero copy because the data's in one place and you just do a load store operation to it. Access the data where it is.
I just meant for the tiering. If you actually move things from one tier to another, you actually need set aside space somewhere.
Correct. Yes.
To do that. Yeah.
Sharing assumes at least a single level of media, right? So everybody's the same. It's just gigantic, right?
That snapshotting can open a whole area of data protection.
Exactly. All the RAS, the data protection, the migration, the resiliency. Yeah, it's all the same reasons that storage snapshot exists today. We're just doing it with
storage and memory and concepts.
Yeah.
I'm saying take my old documentation, wipe out storage, and put in memory.
Yep.
About the shared or the pooling of the memory, which is great, but it also opens up a world of pain in terms of security, right? If you have have memory access to other hosts and all that. So how does the memory manager or memory machine deal with still restricting access so an application cannot read memory from not another application, but also from another host?
So we are reliant somewhat on the CXL hardware protocols to do a lot of that security model from a endpoint perspective. But it's no different today than the security models we have with containers and VMs, right? I mean, you can have multiple instances of applications running on the same host. They're all accessing the same DRAM. That's not a MemVerge problem to solve.
No.
Perspectively. But yes, I mean, we do take security seriously, but we do rely on the security models that the underlying or technologies above us kind of implement.
Okay. And so, if I'm correctly, CXL does not have the security feature in this version yet. It's in
Correct.
2.0.
Yes. 2.0, 3.0 introduces some. I think newer versions of the CXL spec will introduce it. But the device vendors are also, security conscious, so they're able to implement some of these security models into their devices if we need to. So the path, as we see it, for moving towards the CXL Futures. So the diagram on the left is where we are today. It's just a bunch of servers in a rack. They have DRAM, and some of them may have CPUs, GPUs, accelerators, whatever they have, right? The emerging ones, the two in the middle, that's where we've just been describing between all of us today, where we can now introduce CXL locally into the host and expand memory capacity, memory bandwidth for applications as well. And then as we go into the switched environment, right, we talked about JBOMs and appliances. So now you can imagine each host doesn't need as much memory, local DRAM, because it's locally or remotely available via the pool, I should say. And then as we get into the future and we get into multi-level CXL switches, we might get CXL GPUs, network cards, that's the type 1 and the type 2 devices. So those could potentially go into their own JBOMs. And now you have a fully composable data center where you just have dense compute nodes with just a small amount of DRAM. Memory is external in pools and they can all access it. And your GPUs are sitting in a GPU box, right? And then as we get into peer-to-peer in CXL 3.0, now the GPUs can access memory, they can access memory in the rack, they can access memory down the row in the pod. It opens up a world of opportunities for us.
So is software like MemVerge required for a system to be able to access the CXL memory pools, or is that handled by the memory controller in the CPU?
It's a little bit of everything, yeah. So the hardware is the ability for a CPU to access CXL and GPU to access the memory remotely. We are offering the abstraction layer for applications that need it, but also the composer is the thing that will go off and say, I'm going to launch a Kubernetes environment. It's going to need X amount of memory. It needs X amount of GPU. Tell us about it. We go off, ask the switch to go and plumb up the necessary links, ask the JBOM for some memory, and then compose it up to the host or hosts that have requested that. So just as we described, right? So there'll be a bunch of data services, agents, so to speak, that live on each of the compute nodes. We can talk through our MemVerge composer on the control plane to each of the devices in turn, again, if they're SLDs, MLDs, DCDs, request the equivalent memory, GPUs, etc. in the future, and compose that up to the applications. The bit top left, the data center management, there was a great question, I think, Craig, you asked earlier about, how do we use it, right? But we don't want to come in with a brand new management tool for your data center, right? I mean, if you want to get it, that's fine. But we want to integrate into your workflows, into your existing tools. So it becomes a natural extension of what you're doing with your data center today. And that's the MemVerge plugin piece. So, if you're using Terraform, for example, we can write a Terraform plugin that says, hey, if you want memory, we'll request it from our composer. The composer will go off, do the necessary action through the Fabric Manager to compose that memory to the hosts. And then you can do whatever you want on top of that. If you want to launch your Kubernetes, your KVMs, whatever, that's fine. So we talked about some of these value props, right? The reduced expenditure, data center consolidation, do more with less, optimize your memory usage. You're no longer with stranded and frigid memory because we can do composability, we can do thin memory provisioning. And if you can give applications more memory, depending on the application, hopefully they give you faster time to insight, right? You can reduce your latencies on your database queries because you can cache more data in memory, right? So, and the simplified memory management is what we just described with the composer. So where we see this enacting, at least initially, the FSIs are really interested in this because their data models are getting pretty big from a fraud detection perspective. They're interested in pub/sub for trading applications. If you can do that in shared memory, now you don't need all that network stuff that goes on. If you can get those latencies down, say from 1.5 to 2 microseconds into the nanosecond range, that's a significant win. Preventing out-of-memory conditions. In the AML space, again, their models getting big, just need loads of memory. So if we can move more memory into those nodes, that would be great. Public-private cloud, we've talked a lot about, again, reducing the stranded and the frigid memory, memory bandwidth, different memory classes, offering that out at different price points to the end users. And then for HPC, again, they're probably looking more at the pooling, sharing kind of features to reduce the MPI traffic over the network that they currently suffer with today. So,
what real world use cases have you seen with the memory snapshotting technology? I know there was something around spot instances with AWS. Can you go into that just a wee bit more?
Yeah, so that what you just mentioned, the spot instances, is what we call MMC, or Memory Machine Cloud Edition. It is the ability for you to run your same long-running application instead of doing it on kind of hardware that you either pre-provision and get cheaper costs because you're buying it, annually or biannually. You can now run that on spot instances at like 80-90% of the cost. And what will happen there is, the reason spot exists is because they can take it away from you at any moment, right? They give you, depending on the cloud vendor, you might get anywhere between 30 seconds and 2 minutes warning of going, hey, we're going to yank this from you. You best shut down your application. And we intercept that signal. And we go, okay, we're about to get yanked off of this box. Let's take a snapshot. We save that down to your block storage, S3, for example, EBS. And then we will use in the scheduler, we will reschedule that job using the snapshot on another instance. So as far as the application is concerned, it just keeps running, right? And you're saving that 70-80% minus the license fee and stuff like that. So that's a great benefit for snapshots. The other place is bioscience, for example. So, with all COVID and everybody kind of looking at the genomics of what the COVID is doing, the typical pipeline is very serialized. And that might run for days and weeks of analyzing your genomic sequence of different drugs and mutations and all that type of stuff. Well, using the snapshot and thin clone provisioning that we have, we can take at every pipeline a snapshot. And then the scientists can say, well, for this new run, I want to change this DNA sequence. And for this run, I want to change that DNA sequence. So then you're starting to get this parallelism. And you can take a workload that would take multiple weeks down to hours or days, because now you're able to do stuff in parallel. So two examples of where snapshot works, and there are many more besides. So,
I guess in the Kubernetes world, I don't know if you know this or not, but I guess they're probably working on something similar to storage classes, and they'll bring out memory classes, and that would align with the tiers.
Yep.
And so dynamically provision memory could be, memory class, gold, whatnot. That's why I see that might be going. I could be right or wrong.
No, we see that too.
Oh, good.
So
I was guessing, but
your storage class interface. We see a memory class interface coming, right? A bunch of APIs that allow you to manage the memory for that. So.